So today we kind of want to talk about constant and changing velocity graphs, kind of different situations that you might see them in, also how to interpret the graphs and how to know when you see certain things, understand what's going on. And we're going to do some practice problems at the end and then eventually let you go and graph on your own. Here's some examples of constant velocity. So in physics, we're going to always pretend certain things happen just to make our lives easier. So the most classic one is walking at 2 meters per second, or you're driving at constant velocity. In reality, there's a bunch of forces acting on you in order to have that. But for all these cases, the forces are balanced. So the net acceleration is 0. There are accelerations, but the net one's 0. So for the beginning part of our problems, we're just going to assume there's no acceleration, or acceleration equals 0. So when you're walking at 2 meters per second, constant. Driving at 10 miles per hour, constant. On ice, we're going to pretend there's no friction. So let's say the penguins are sliding, they're going to slide forever, but in reality, they do slow down. Skydiving eventually hits something called terminal velocity. That means the forces of gravity down equals the forces of air resistance up, and you kind of don't accelerate anymore. I think it's about 200 miles per hour. That's kind of where you hit terminal velocity, and you'll fall down at that speed and not go faster. So that's why in movies you can see them kind of when they're in that sprawled position, they're not going anywhere. But if they're trying to save somebody because you're in a spy movie, they'll kind of get into a tuck position and fly much faster. They're reducing their air resistance so they could go a little bit faster. But all these situations, you're going to have constant velocity. But like I said, in the real world, everything's changing velocity. We have an imbalance of forces. And when you see something falling, that means gravity's winning. So we have acceleration of gravity. Rolling down the slope, same thing, gravity's winning. So you have acceleration of gravity. When you're throwing up, even though it's going up, you're going to have gravity pulling it back down. When you're driving in a horizontal direction, when you push on the brakes, your brakes are slowing down the car. When you hit on the gas, your engine is pushing the car forward. So these are examples of changing velocity. And we're going to see a curve versus a straight line. All right. So what to expect when you see these? And I'll try to make this as clear as possible. For straight line, there's 3 possibilities. You have 1, 2, 3. Okay. You could have a straight line up, and I'm going to purposely go below the x-axis just to kind of emphasize the meaning of this. You could have 0, which we could pick, let's say, up here, and we could go down, right there. All right. It does not matter where in a position versus time graph, or a displacement versus time graph. That's a D, sorry. It doesn't matter where it is on the graph. Where it is just tells you where your starting point is, but it doesn't really affect the velocity or the speed of it. So when you have a positive slope, even though it starts from here, it's the same thing as if it started from here, motion-wise. What it's doing in real life, it's starting at a different place, but motion-wise, it's doing the same thing. Here, you are doing positive constant velocity. Here you have 0 constant velocity. So even though it's 0, it's constantly at 0, so we could say it's constant 0. And here you have negative constant velocity. So we have either, let's say, somebody moving forward at 2 meters per second, somebody at 0 meters per second, someone going backwards at 2 meters per second. So that's what's kind of happening. The magnitude is the slope, which we're going to ignore for now. We're just going to kind of talk about in general what's going to happen. What else you can see is a curve. And curve means changing. If I can spell. Velocity. 0. So there's going to be 4 different situations that you can see here. So I'm going to try to fit them all in here. And this is the hard part, which some of you might just memorize, but some of you could probably reason out. This is what we did that first day with the rocket. Here's another one. Let's do, what's a good color? Purple. Then you could kind of have the first one, but just a flip of it. And then you could kind of have the second one, but also a flip of it. Okay. So when you're looking at this, and then we'll kind of explain what these are, but these are different types of graphs that you can see when it's a curve. I purposely did some purple and some pink. You'll notice here that if there is a slope, which I'll kind of explain how to get, these are all positive. And if you look here, they're all negative. So towards the end, we'll kind of explain how to get this. So right now, these are kind of the things that you'll see. So the key thing to look at for D versus T graph is slope. Here's all the different possibilities if it's a straight line versus a curve. Now for us, we're going to always say it's going to be a nice smooth curve. We're not going to have anything crazy that looks like this. Okay, in real life that could happen, but for us we're going to not, because this requires calculus, which we're not going to do. So everything here we could solve algebraically, so that's how we're going to keep it the way it is. Okay, so this is kind of where I was leading at. Constant velocity, we can have an example which is 0. So 0 means we don't have any acceleration, and it also means it's constant. So that's when you have a balance of all forces. Technically, when you're in outer space, when you're far enough from every planet or star, there is no acceleration. But that's very, 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 very rare situations where you're in the middle of absolutely nowhere. For us, we're always going to have the sun really doing something, so that's gravity. And the sun pulls at a constant rate, at least for us on the surface on Earth. Technically, as you get further and further away, which we'll calculate once we get into circular motion, there is less gravity. But for most cases, within our atmosphere, it's going to be 9.8. Non-constant is real life. When you have air friction. When you're walking at 1 meter per second, you're not going to feel the air push slowing you down. But if you're going at 50 miles per hour or about 30 meters per second, 25 meters per second, you're going to have a really hard wind pushing against you. So if you ever ride your bike towards the beach, one way is much easier than the other, depending on where the wind is, whether it's on your back or on your face. Most acceleration of cars are going to be non-constant, because even if you floor it, the engine takes a while to get started. It's going to hit a peak RPM or peak power, and that's where it's going to push the car the most. Even in a fancy electric car, a lot of acceleration in the beginning, and then towards the end, there's not going to be as much. So cars, even rockets, they all have different types of acceleration. But we're going to usually say, we're going to stick with constant, just because, like I said before, if it's changing, we're going to have to deal with calculus. We're not going to deal with calculus in this class. So everything's going to be constant for us. So how do we get the slope of a curve? Slope of line is pretty easy because it's just one slope. But if you have a slope of curve, that slope doesn't do it justice. So so what we want to do is find the slope of a tangent and repeat. The non-graphical way is to do calculus, which I might show another day, but not today. So this is kind of the graph that we had from the other day. This is of the SpaceX rocket launch, and this is not a straight line. So if you get a line and go, okay, my best fit line is, I'm going to do my best to do a straight line. Oh, I think I can do a line on this thing. Okay, so let's say this is my best fit line. Kind of right? Some above, some below. I say a good average. And then if you find the slope of this, let's pick out 2 points. So the finest slope here is 1 point, and this is close enough. Let's do an estimate. So the rise is 0.5 kilometers. The run is, let's see, each one is about 3.3 seconds, about 6.6 seconds, I think. Yeah, looks like this graph is 6.6. So here, this is our acceleration. But that means it's the same here, here. And we know it's not true. And we know it's not true because when we look at the rocket launch, from 0 to about like 9, it really doesn't move. It just sits there because the whole time that rocket has to overcome gravity. It's building up force in order to get more faster and faster and faster and faster and faster to push up against gravity. I mean, it might like lift up a tiny bit, but from far away, it ain't really moving. As the rocket gets burned more and more, it's accelerating faster and faster and faster. So we know this is not true. As the rocket goes up, it's not a constant velocity. So to be more accurate, what you could do is to do multiple tangent lines. So a tangent line is a line that crosses the curve only once. So in the beginning, you kind of do, okay, a tangent line in the beginning looks more like that. So you'll notice right here, it crosses, oh, what did I do? Okay, it crosses the line right here. Now, if I want to adjust it a little bit better, let's say I want to get it at that seconds, then I'll draw a line. Let me change the color this time to red, and I'm going to draw it like this. I wonder if I can move it up. Nope, I can't move it up. All right, but let's imagine it's there. Let me try to do it one more time. It's kind of harder than it looks. All right, there we go. So there's one slope right there. I'll do another one. Let's do orange again. One in the middle. And then one towards the end. So this is what we're going to do for practice today, is drawing tangent lines. And then, let's see, I think I can catch it right here. There we go. Okay. And then let me get my pencil, do black. So here it crosses right here at one point, the orange one kind of right here, and the red one around here. So I drew 3 tangent lines, and then you're going to have a kind of a good estimate of what's going on. Here I could kind of already guess the slope is 0 kilometers per second, so it really isn't moving in the beginning. Here it looks like here's a dot, kind of crosses the grid, and we'll estimate again here and here. So the rise is 1 kilometer, and the time is looks like about 16 seconds. And then the red one, let's see, it crosses here and it crosses, and we'll estimate again just because we're doing this on a computer. About 13 seconds is the change, and the rise is 1.5. So if I grab my calculator, oh, there's my calculator. All right, if I grab my phone, okay, 1 divided by 16 is about 0.0625. 1.5 divided by 13 gives me 0.115. Okay, so it makes sense. It's going from 0 to 0.0625 to 0.115 kilometers per second. Now, if you want more accurate reading, then what you would do is do more tangent lines. When you're doing something like this, I like to at least have 3. Having 2 isn't very useful. 3 is okay, 4 is probably better, but we don't need to do a lot. You don't need to do one at this. The cool thing is once you learn calculus, you could find the slope at any time without drawing a graph. So that's the power of calculus, derivatives, integrals, and things like that. Hopefully that makes sense. That's kind of what I want to say. And then eventually, kind of what you're more responsible for is, I found this on the internet where I thought was great, is when you see a velocity versus time graph, you should be able to describe what's going on, kind of the same way you see a displacement versus time. So the more we do, the more we're going to get. And a page like this one, where I had all the things up, will make more sense. So I'll have kind of like a PDF, kind of a summary of all of this as well. So hopefully that helps. Let me know if it doesn't. Take care.